Welcome back to one of the videos where we're going to be going over applications of the integrals. This application is called average function value. Basically, we'll be looking for the average integrals in this case. And here's the question. If I'm giving a graph of the function, here it is, f of x, y equals f of x. And I found the integral of that function from 1 to 9. That will be this area. Here it is. And now I have a question. If I found a total area from 1 to 9 below this graph, can I figure out what was the average area? Well, first of all, why is this question even interesting? Imagine if this is the graph of the velocity and we integrating the velocity with respect to time from 1 to 9, say, minutes. Integral of velocity, gives you the distance you traveled. So this area told me the total distance I traveled from 1 minute to 9 minutes with the given velocity y equals f of x, which we usually call v. So the question is, what was my average distance? What's the average distance I traveled? Because at some point I traveled a lot because the speed was very fast. At some point I traveled much less because the speed was very slow. So what was the average distance traveled? And the average, it's somewhere in the middle, kind of. You're thinking, it's probably the average. So I will make a guess. I will draw a line and I will say probably the average for this area is like over here. So I will say average was, maybe 10 for the whole thing. So the answer for this integral will be a finite number. Say it was 35. So I'm like, maybe 10 or 15 was the average. That's the guess. On average, I was traveling 10 miles when I was driving with this changing speed, but with a fixed time from 1 to 9. An interesting idea that to figure out this average, I will have to take whatever is above the average and below the average, and those things should kind of match up. Look what I mean. Here's the answer. The actual average is over here. So it was actually not 10. It's actually close to 10. Look at that. I accidentally guessed. Around 10. And the average means that this line, the dashed line, which gives you the average function, will average up the hills and the gaps above and below the average. So what it does, it will take the upper hat over here, the extra pieces where, say, the speed was really, really fast. And then it will put them here, and they're supposed to balance each other out, and you get a perfect rectangle, and that's exactly the average. Because the average speed, say I was traveling on average, say with a speed 5 miles per hour, that means it's fixed, right? So in this case, say it's 10, then it means that this is a constant function. Constant function is a vertical line. So that's the idea of the average. Here's a very nice animation which shows you how it happened. Actual average after my wrong guess, my guess was actually not too bad, is around 10, and you see how it balance each other out, the pieces above the average and the pieces below the average, and that's how you get the average. So it's basically, if I'm asking how many people in total got sick, if this graph shows me how many people are sick every day on day 1, 2, 3, 4, 5 until 9 days, the area below the graph will give me total number of people sick for these days from 1 to 9. But what was the average number of patients accepted to the hospital which were sick? The average will be somewhere in between the maximum and somewhere below, right? So this is how you see what the average is. The average has something to do with the area, that's why we will be integrating, but it also will have something to do with the length of the interval, because if I'm asking for the average from 1 to 5, the average will be different. Here's one more example. And this actually looks like some statistical data. And average functions are very popular in statistics. As you can see, we have people, and on the y-axis we have age of those people. And then seems like from the data we collected for 10 people, the average age was 15, even though some people were older and some people were younger. So that's the thing. If they call it actual average, because originally it was a game for students to guess, and then I was supposed to reveal you the actual average. So it's pretty cool and very makes sense how the pieces above the average, they balance out the pieces below the average, and it becomes the exact rectangle. Now let's work on the homework examples. After of course, I will show you the formula. And this is what you need to know. You need to know that the average value of the function f of x over the interval a from a to b is just the integral. Is just the integral from a to b, but then multiplied by the average of the interval, 1 over the average of the interval, and that is 1 over b minus a. That makes sense. Basically, we want to know how many people were sick on average from day 1 to day 9. Then I want to check what was the total average. First, the total average, say, gave me 1,000 sick people. And then I will divide by 9 minus 1 days, and that will give me the average number of sick people. Make sense? The average number. So, first example is just some blank example about the function with no literal application, and the other examples will have amazing applications on this. Find the average value of the square root function, f of x square root of x, on the interval. We'll look at the formula and let's just follow the formula. So f average, that's not actually international notation, if be honest, and I saw different notations on this, is going to be 1 over 25 minus 0. Always find the exact length of the interval. It's not always the same as the b value, you will see later. From 0 to 25 over the square root of x dx. Well, the number in front of the integral is 1 over 25, and now let's integrate square root of x. If you're not sure how to do that, rewrite it as x to the 1/2. Integral of x to the 1/2 is 1/2 plus 1, that's 1/2 plus 2 over 2, that's 3/2 over 3/2. If you're already good in integration, then you know that when you divide by this fraction, you actually multiply by the reciprocal right away. That will save you some time. So we're dividing by 3/2. That's the formula of how to integrate x to the n dx. Add 1 to the exponent and divide by the number you got, plus c. For the definite integral, instead of plus c, I will have a bar from 0 to 25 equals 2 over 75. That's 25 times 3. And then I will have top minus the bottom, 25 to raise to the 3/2. That actually means I will square it and then find cube root of that number, minus 0. And the final answer will be 250 over 75, which is 10 over 3. That's the average value. That's the average value. The exact value was the same answer, but without multiplying by 1 over 25, right? So average value only has this piece in front of it. That's the whole difference. Every time we ask you to find average value, that means you should not forget to multiply your integral by 1 over b minus a. So that means that exact, just note, I will make note in blue. Exact value is just integral from 0 to 25 square root of x dx, and that will be 10 over 3, but without dividing by 25, so I will multiply by 25. That's 250 over 3. So that means that the area was changing, and this is my total area below the graph of square root of x, 250 over 3. But the average is 10 over 3. Very interesting idea over here. From 0 to 25. Second example has pretty cool application. A car was driving down a road in such a way that its velocity in meters per second at time t in seconds is given as a function v of t, 2t to the 1/2 plus 3. Find the car's average velocity to 3 decimal places between t equals 2 and t equals 4. Now you know what's the difference. We just want to find here average velocity. I will call it v average of t, and I know that's just normal integral from 2 to 4 of the function we're given, vt to the 1/2 plus 3 dt, but we're also dividing by b minus a, that's 4 minus 2. Let's start. So I wonder, I was driving fast and slow, what was my average speed? That's the idea. 1/2 in front of the integral, and now I'm starting integrating. 2t raised to the, we already know this, 3/2 times 2/3. 2/3, we had this before, plus 3t bar from 2 to 4. I will have 1/2 in front, and I'll have 4/3. Then I'm plugging the upper value, which is 4, raised to the 3/2 plus 3 times 4, parentheses minus. Be very careful. If you want to factor out this 1/2, then put huge brackets outside and make sure that you have separately plugged top and separately plugged the bottom of the limits of integrations. Then don't mess up with parentheses because of this negative sign in the formula and because of the constant in front of everything. When I'm plugging 2, I will have 4/3, but now 2 raised to the 3/2 minus plus 3 times 2. What is 3/2? 3/2 is cubed and then a square root. So 4 to the 3/2 is actually 4 square roots and then cubed based on the properties of exponents. Square root of 4 is 2. 2 times 2 times 2, that's 8. So actually the first piece over here is 8. And so on and so on. Keep calculating and you'll get the nice answer, which is, what I got was 1/2 32 over 3 plus 12 minus 4/3 square root of 8 minus 6, and that's approximately 6.448. That's what it is. Average velocity was in meters per second. Meters per second. So that was my average speed. One more example. Example number 3. If I give you a temperature in degrees, in Fahrenheit, do I say it right? I always say it wrong. Fahrenheit, because I work with Celsius, okay? I'm a fancy European person. T hours after 12 p.m. is modeled by the given function. F of t is 60 plus 12 sine t. Find the average temperature from t equals 0 to t equals pi. Let's do that. Basically, what they ask me to find is average temperature. And that's going to be this integral from 0 to pi. That's what they said, right? And of the function they gave me 60 plus 12 sine t. But that's going to be the total thing. To find dt. To find the average temperature. That's important. If we don't say this phrase, average temperature, then you stop here and you can keep integrating. But the average temperature have this extra piece, 1 over pi minus 0. Let's do that. 1 over pi is in front of the integral. Let's start integrating. 60 gives me 60t. 12 sine is negative or positive cosine. Indeed, it's negative 12 cosine t. If you're not sure, differentiate negative 12 cosine t prime gives you minus 12 sine t. That's correct. Bar from 0 to pi. Let's plug it everywhere. First, I'm gonna write down 1 over pi and start plugging pi everywhere. 60 pi minus 12 cosine pi. And that's only the first part, the top, minus plugging the bottom. 0, because 60 times 0, minus 12 cosine of 0 is not 0, so be careful with that. So I have the top function plugged, not the function, the upper limit of integration plugged, the lower limit of integration plugged, the difference between these two, and everything multiplied by 1 over pi, which is basically the average of the interval we are integrating on. So let's calculate carefully everything. 1 over pi. We have 60 pi minus cosine pi is, I know that cosine of 0 is 1 and cosine of pi then is negative 1. So it becomes plus 12. Check your trigonometrics. Minus 0 minus. I will wait about that first. First I want to check this. Cosine of 0 is 1. So minus and minus 12 gives me plus 12. So the final answer will be 60 pi over pi, that's just 60, plus 24 over pi. That's the exact answer, and that's the exact average temperature, which is approximately 67.639 Fahrenheit on average. Last example is hiding over here, number 4. And this one is application in physics, and we're working with the linear density of the rod. Density, you know what it means, like how strong basically the rod is. Is it like a rubber or like a metal and so on. So the density, linear density in a rod 3 meters long is given as a function where x is measured in meters. So the longer it is, the different density we get. And in this case, the longer the rod, the less density it is, because we're dividing by 1 over x squared. From one end of the rod. Okay, find the average density. This average gives me that I will just build the integral, and then I will divide by the length of the interval we are integrating over. Density, average density. Oh, okay, I will call D. I have no idea how in physics they code, so if you're a physics major, you should know better. Equals integral. It says 3 meters long. That means I'm integrating from 0 to 3 the function 10 over 1 plus x squared dx. There's going to be the total density. But if I want average density, I will divide by 3 minus 0. And it's going to be 1/3. Is it 1/3? Nope. You see this 10? I will kick it out. So it actually will be 10/3. 10/3 integral from 0 to 3, 1 over 1 plus x squared dx. Looks scary, but do you remember this function? It's actually pretty simple. What gives you 1 over 1 plus x squared when you differentiate that? Yes, it is arctangent. Who said that? Or tangent minus 1. Or inverse tangent. All of these things means the same. 10/3 tangent minus 1 or arctangent of the top minus the bottom. Look, I'm gonna skip the whole step. Arctangent 3, and I'll put brackets, minus arctangent of 0. Top minus the bottom. Skipping the step here. Top minus the bottom. Nice. Okay, I know that arctangent of 0 is 0. Can you think why while I'm writing? So the answer will be just 10/3 arctangent of 3. That's the exact answer for the average density, which is approximately 4.163, and it was measured in kilo per meters. So why arctangent of 0 is 0? Arctangent is tangent of what gave me 0. Well, it's tangent of 0 or pi, 2 pi, and so on, but we are working on the restricted domain. On the restricted domain, the unique answer is 0. That's how you always should remember how to work with inverse functions, inverse trigonometric functions in this case. So that was the last example, and as you can see, we have tons of applications when it comes to average functions. Average density, average speed, average temperature, average anything you think about. Basically find the typical integral you think you can find on the interval that we give you, and then divide by the length of this interval. And it makes sense that it will give you something average, whatever we're asking you to find, whatever you're integrating. Great job for watching. Hopefully you enjoyed it. It was not too bad, but definitely it's a very good practice of integrating different functions. See you next time.